existing. That one's lost to time. And what we're going to start with today is we're going to have two short presentations. One, Debbie Bard is going to start by describing how to work with NERSC. And NERSC is our primary compute center for DESC and dark energy science collaboration work. And so Debbie will walk through how do you work at NERSC, how do you use the batch systems, how do you actually do your science using NERSC resources. And then Jim Chiang, and I think he's going to be ably assisted by Phil Marshall, are going to introduce something that came up when we were talking about the computing and infrastructure reports for software and how do we develop software and do science as a project, which you'll hear about these reports tomorrow. But one aspect that kept coming up is the need to have our software that is both readable and understandable. And readable and understandable means not just to readable and understandable for us, for the next day, but it means readable and understandable by other people in your working group, and also yourself to be able to come back several months later to try and understand what it was that you were doing and why. And so Jim is going to introduce some tools that may make it easier for us to make our software both understandable and readable and shareable. And he'll introduce some of those and show how we can use tools such as code reviews to effectively get two people to look at a piece of code. So getting a second pair of eyes to look at an analysis code that you've done. And there are lots of examples, both in industry and in science, where having multiple people looking at a result makes it more robust and makes it better science. So I'm going to turn it over to Debbie, and she's going to start us off.
Good. All right, so as Andy said, I'm going to give the first in our tutorials this afternoon. This is a very basic introduction to NERSC, the National Energy Research Scientific Computing Center, which is at Berkeley Lab, just over the bay from here. So this is a very basic introduction. Anyone who's used NERSC already will probably be familiar with most of the material. I'm going to start by sort of going over a bit of NERSC jargon, because there are some terminology we use at NERSC that isn't always familiar. I want to talk about what resources are available, so what compute systems, what file systems are available, what you might want to do with your data, where you might want to store your files, store your data, store your compiled executables. And then, once motivated, why you might possibly want to be using NERSC, how do you get an account at NERSC? And this is well documented on the Confluence page. It's a straightforward process to get yourself an account at NERSC. Then I want to go through what you see when you log in, what the login nodes are, how you actually interact with NERSC once you have an account. And then I'm going through a very simple example of how to submit a job to the batch system and talk a little bit about the different ways that you can use the batch system. And I should say, again, this is an introduction, and more information is going to be available on the slide deck that's linked from the meeting webpage, the tutorials Confluence page. There's two slide decks linked there, one which is this slide deck and one which is the full slide deck, which is nearly 90 slides of information. And so if you have sort of more questions or want more background, more detail on any of these, then that full set of slides is probably a good place to start. And also, asking us these questions is also a good place to do it. Okay, so I just want to start with talking about some NERSC jargon. To start with, you all are users in our eyes. We call all of our people who have accounts at NERSC users. So I'm aware that I use that term quite frequently without really explaining what it means. Probably the most important term to describe here is repo. This is an old-fashioned jargon that comes from NERSC 20, maybe 25 years ago. Repo stands for repository, and it's not a Git repo, not a Git repo, not a GitHub repo, not a Bitbucket repo. It's a repository, meaning a project which has been allocated resources at NERSC by the DOE So in our case, our repo is the LSST DESC repo. So just be aware that when we're talking about repo, we're talking about the project, not necessarily your GitHub repo. MPP is another phrase that comes in. This is another sort of hangover from the old days. MPP means massive parallel processing. And we talk about MPP hours, and I'll mention this later on. And this basically means compute hours. So MPP just stands for compute in this context. I'll talk a bit more about our batch system later on, the Slurm batch job scheduler, and we use the term partition interchangeably with queue, which might be new for you, and that's sort of a logical way of thinking about how the compute systems are partitioned into different resources. Other words that come in, we talk about compute nodes at NERSC. A compute node contains many compute cores. So when you're running jobs, you will want to think about whether you want to use an entire compute node or a subset of the compute cores available on that node, depending on whether your code runs on one thread or multi-threaded or however you've got your code set up. A similar term is inode, which is an index node, which this simply is a file system object, but we have limits on the number of file system objects, on the number of inodes that you can have in any of your disk spaces. So that's something to be aware of. And something that I'll refer to all the way through this is a ticket. We have a dedicated team of consultants at NERSC who will on hand to answer any and all of your questions. We often refer to this as filing a ticket. If you submit a ticket to the NERSC help desk, then you'll get help within a couple of hours from the NERSC consultants to answer more or less any of your questions. So as you're going through your adventures at NERSC, don't hesitate to submit a ticket to the NERSC help desk if you have any questions about any of the systems. Right, so I'm going to start off by going over very briefly our compute systems. NERSC currently deploys what we consider separate data-intensive and compute-intensive systems. So without wanting to go into too much detail about this, the compute-intensive systems are ones where you might run, where we encourage people to run massive MPI jobs, massive parallel jobs that run over thousands or tens of thousands of compute nodes or compute cores. So these are not the kind of jobs that perhaps we will be running as a collaboration. We're much more likely to be looking at the data-intensive side of the NERSC resources. By that I mean Cori Phase 1. You're probably going to be using Cori Phase 1, which is our new supercomputer. It was installed in the fall. It's been available to users for the last couple of months, and it's what we consider our data partition. So it has a number of hardware features and configuration features that are designed to be useful for data users. So people like us who are running jobs that are perhaps very low in the level of parallelism. So single thread, single core jobs, or sort of few core jobs rather than these massive MPI codes. So I'm not going to go into all the details about the configuration of Cori Phase 1. There's probably only a couple of things that are really relevant to you. One is that the memory, we have 4 GB of memory per compute core for running your applications. So that's something you'll want to bear in mind. And there are ways of having more memory per core if you've got a very memory-intensive code that you're running. But that's, as we average out, we have 32 compute cores for every compute node and 128 gigabytes of memory per compute node. So this is just what it comes down to. And you also have the choice of operating system. Now, something that people don't always realize with supercomputers is that we have very optimized operating systems, something that is designed to function well with the hardware of the supercomputer. And that includes a lot of communication between the compute nodes. But there is a choice of Linux operating systems in Cori, and a choice of compiler versions as well. So you can use the GNU compiler, which is something that's available for everyone, or you can use one of these Intel or Cray optimized compilers. So in general, you're going to be using the standard compilers that you use on your laptop, that you use at your university compute cluster. You'll be using that compiler probably at NERSC as well, and that should work out of the box. You shouldn't see any differences with that. That's a good question. I do not know the answer. Yeah, it's not a question I know the answer to.
Can I ask a question?
Yeah.
Is the Linux operating system choice that you know about, is that a user choice or is that a setup choice of you guys?
It's a setup. Okay, so without going into too much details, you can use CHOS, which is change operating system, and to switch into a different operating system. Now, I don't know how functional that will be. It exists and it functions, but I don't know how optimal your performance would be using that. It's not something I have a lot of experience with. And I'm not sure, I don't think I would say that it's recommended use, because I think that a lot of functionality is not available in the standard operating system. But it is something that exists, and I can come up with pull out some more documentation for that. The default one you get is the Cray optimized scientific Linux. Okay, so so those are the compute systems, the file systems that you can access. The first thing I need to say is the thing that everyone will tell you whenever you're starting to use any compute system is protect your data, back it up. Some file systems are backed up, some are not. It's easy to forget what is backed up and what is not. It is very easy to lose data if you're not paying attention. Restoration of files, if they're purged, if they're deleted, as part of our system-wide file purging, it may be possible to retrieve them. It probably won't. Hardware failures and human errors happen. We had a power work gone on 2 weekends ago, and during that power work, there was a fault, and one of our disk enclosures caught fire. None of the disks were damaged, but it could have happened. So this is a real sort of reminder to me and to everyone that hardware failures can happen through no fault of anyone in particular. So back up your data. Don't assume that if it's there, it's going to be there forever. Although I will say we haven't lost any data in a very long time. But so the file systems, this is simply taken from this web page on our NERSC web pages. I want to go through a couple of details of these. One is that there are several different types of file system. The one that you see when you log in is in your home directory, and that's 40 gigabytes of quota and 1 million inodes, and that's basically unchangeable. That's your quota, and that's what you get in your home directory. And so we recommend people do things like building code in your home directory or storing configuration files. It's not really got very good access. It's not got very fast I/O, but it is great for storing configuration files. The project disk space is allocated by project. And here we're using project instead of repo, which I realize gets confusing, but each project has its allocated disk space. And this is the path to the LSST, to the DESC project space. We have, as a project, as a repo, about 90 terabytes and 5 million inodes as a quota. And depending on the usage, some of you may be aware that this sometimes gets filled up, but sometimes there's a lot of space available. The idea of the point of the project disk file system is that it's designed for data that's accessible to the whole project. If you have things that you're working on individually, things that don't need to be accessed by the whole project, then you can put them in your scratch space. And your scratch space on the Cori system is very nice. So you get, as a default, 20 terabytes and 10 million inodes on your scratch space. And it's also very fast. So the access speed for project is something like 40 gigabytes per second, whereas for our scratch space, we have a really nice brand new Lustre file system, and we're getting something like 700 gigabytes per second. So the downside of the scratch file space is that any files that have not been accessed over a 12-week period are going to be deleted. We have a purge policy in Scratch. So this is where you have to think about how you're going to deal with your data, what you're going to put in different places, how you're going to use the resources, how we as a collaboration are going to use the shared resources, and always bearing in mind that you'll need to back up your data. Yes?
Because what you're showing the LSST.
I have this information in just a couple of slides of how you can join the DESC repo. So when you're thinking about where you're going to put your data, these are the sort of things to think about. That your home, it's got very poor I/O. You don't want to use this in the batch system, and so you don't want to be accessing it or writing data to it from the batch system. And then sort of figuring out the balance between whether you put your data in your Scratch or in the project space. That's something that you have to think about depending on what you're working on.
When you say only visible to you?
By default.
Right, okay, so if I change my permissions in Scratch,
absolutely, yeah. It is all controlled by file permissions, by POSIX permissions. So if you change the file permissions, then people can access your data, your space.
We make that a project.
That is a thing that can be done. There are tools that can do that.
Yeah, in general, I wasn't sure whether it was a policy or not, but the uname masks and things are set up by default with nobody.
Yeah, yeah. We
policy, or we could change it globally so we could all see each other.
Yeah, so we err on the side of maximum privacy, maximum security, but there are ways of changing that. Okay. Any other questions about the system or the compute resources?
When you say visible on one machine,
yes, yeah. So visible on one machine is which machine you're using. The Scratch spaces will be cross-mounted across both machines, but that's not going to happen until the end of the year. So at the moment, if you're using, and I've only been talking about Cori, of course. We also on Edison, our other supercomputer, there it has its own Scratch system. Where you have a slightly smaller quota and the I/O access speed is slightly less performant. But I haven't really talked about that because I do anticipate most people will be using Cori. Yes.
What about the home? Is it visible on all machines?
Yes, home is visible everywhere. It's visible on all machines. Okay. So I just want to mention this. So when I say back up your data, I mean back it up to tape. We have a really nice parallel tape storage system called HPSS. But I'm not going to go through this in detail. There's a lot of different ways you can write your files to it. We have this nice utility, htar, which tars your files directly into HPSS. We have dedicated compute nodes that do this for you, that have a very fast pipe into the tape system. The information's from this web link here, but the key to remember this is that tape is not the same as spinning disk. It's not the same as flash disk. It's a linear media. And so the way that you use this is going to be different to the way that you use your the regular file system disk space that you have. And the key thing is to group small files together and avoid excessive writes. Because when you're writing to tape, every time you're writing to tape, the tape spins up, it does some writing, and then it stops at the end of a file. And it spins up for the next file and then stops. And so if you have a lot of small files, you've got a lot of stopping and starting, and it just takes forever. And this is a shared resource as well. So while you're using this system, you're blocking the use for everybody else. So we really highly encourage people to use HPSS, but there are ways to use it intelligently. Okay, so we have a lot of information on our web pages at NERSC. And so throughout all this, on the PDF, on the Confluent site, you'll see links to all these lots of pages with useful information if you want more information about this.
I can just say on the previous page, you have to think about Google. So Debbie told me about this, but it is awesome. So everybody should the way to copy stuff in and out to your home directories. With one click, it will put it on your laptop. And I was able to log on using my university credentials.
Yep, so Globus is a really nice tool for moving data around. And in the long version of the slides, I've got a bit more information on how to use that. So someone asked, how do you get a NERSC account? Well, first of all, there's two types of NERSC accounts, your user accounts and the repo account. Really, you only need to worry about the user account. The repo account, the project account, is allocated by the DOE and managed by the PIs, which is Richard and Peter here. So this user account is associated with your login or username. So when you apply for an account at NERSC, this is what you specify. So it's pretty straightforward. You simply go to the NERSC website and fill out a form. And there's a couple of things that you need to specify, like the name of your organization, and then submit the account request, and you'll receive an email with your login information. So then once you have that, then you will want to access the DESC allocation, for example. There's when you log on to NERSC first time, it's strongly advised that you go to NIM. So NIM is the NERSC Information Management. It's nim.nersc.gov, and you simply sign in, and you can do an enormous amount of things from this. This is where we sort of try to give users a lot of power to sort out their own accounts. So you can do things like check how much balance you have left in your allocation, how much disk space you have, change your password, change your login shell, update your contact information, add SSH keys if you want to use that. But also, this is the place where you join the repository, where you join the DESC project. So you look for a box, particular box, and fill in this information. So again, all this is on the slides. I don't think I need to read it all out for you, but this is it's a very straightforward way of doing it. You don't have to necessarily contact anyone at NERSC or bother Richard and Peter in order to achieve this. Okay, so now that you have your account, you've joined the DESC repository, you want to connect to NERSC, and this can be done very straightforwardly. Either via SSH, you can SSH into one of the login machines, or you can use NX. And NX is just something I want to mention because it can be very useful to allow you to work efficiently at NERSC, especially if you are far away or you have something of a dodgy internet connection. So what it is basically is it gives you a desktop. You can log in via NX, and you can get a desktop that sits on the NERSC machine and just projects the image of the desktop back to you. And the thing that's very useful about this is that it compresses and buffers messages from X, so you have much better X experience. So this basically means if you're running any kind of visualization or any sort of interactive tool or GUI on the NERSC machines, you're going to have far better performance using NX than you would if you were just trying to do this through an SSH login. Also, the other nice feature of NX is that it provides sessions, and this means that you can suspend a session without terminating your process. So basically, if you are running an NX session on your laptop and your internet connection drops out for some reason, wireless drops out, if you'd been connected via SSH, that's it, you'd be lost. Anything that you were running would be finished. But with NX, this process continues in the background when you lose your connection. And then once you regain your connection, you go to another computer, you can log back into the exact same session and see whatever you were running that's still sitting there in the session. So that can be a very useful tool. Yes?
So to give you an idea just how great NX is, I was looking at images in ES9 sitting in a bus in Northern Ireland. And I was able to scroll them around, and work in a terminal with like what felt like zero latency. That was just
It's really nice. And we will be soon upgrading to a version of NX that allows you to do this on a mobile device and also within a browser. You don't even need to use the NX server. You can do this within a browser. It's quite neat. So that's recommended. All right, so when you log in, whether you do this via NX or via SSH, you hit a login node. And we have a number of login nodes on each of our computers, each of our supercomputers. They're shared with other users, of course. They're designed for code compilation, job preparation, submitting your jobs from the login nodes. So when you SSH or NX into NERSC, this is where you'll land. Of course, don't abuse the login nodes. That's what we have compute nodes for. It's worth mentioning that the standard dot files, your dots, bashrc, .profile, .login files, etc., are maintained by NERSC. You have no control over them. This is because there's often very important environment that needs to be set up that NERSC needs to control. However, you can write your own personal dot files using the .ext suffix to customize your environment. And if you customize your environment so far that you completely destroy your environment, then you can fix this using the fixdots command. That's actually can be very handy. This brings everything back to default, and so you can start again. Okay, so now you've logged into NERSC, you're on a login node. What do you want to do? Well, presumably you want to run some kind of compute job. So I'm going to go through a simple example of running a Python job at NERSC, because I figure that's something a lot of us do. So let me skip that. So we use a batch scheduler called Slurm to organize the workload on the compute nodes. So if you want to run a job on the compute nodes, then you have to submit a batch script to the workload manager. And the batch script contains directives that tell the system how to schedule the job and a command that will launch your executable, whether it be parallel or single-threaded. Simply using sbatch to launch the job, to submit it to the batch scheduler. And this is what your batch script might look like. So it's a very simple one, and because this is pretty straightforward. And there's a lot of batch schedulers out there, workload schedulers out there. I don't think Slurm is any more or less complicated than any of the others. And so this is what it looks like. Here you have directives telling telling the scheduler which partition you're running in, how many compute nodes, how long the job will run, the name of the job, and then srun your executable. It's that straightforward. So this srun is required to launch the application on the compute node. So this is this is pretty straightforward. I mean, there are a lot more complicated examples on the NERSC web pages from this link here that you could look at if you wanted to do a very complex workflow or take advantage of some of the special features of the NERSC supercomputers or of the Slurm system. One thing that's worth mentioning is that you can run parallel jobs interactively. There's a 30-minute limit on this. You can run jobs interactively using salloc instead of sbatch. And then again, you request the resources, and then you can do whatever you want with the compute node. So you can run jobs interactively. So I mentioned before that we have 32 compute cores on every compute node. We have a special queue for running jobs that you do not require all 32 cores on a node. This is called the shared partition because each compute node is shared between multiple user jobs. So the way that you run this job is pretty straightforward. You simply submit to the shared partition. You might want to specify how much memory you require. If you require more than 4 GB per core memory, then you'll want to specify that because this is where that becomes important because by default, every core in the shared queue gets 4 GB of memory. And then you just run your job. It's pretty straightforward. Okay, when you monitor your job, you'll probably be curious about how your place in the queue system is progressing, and there's plenty of resources available to do that. Your job will start when resources are available, so if the system is very busy, then it will take longer for your job to start executing. And your jobs are charged. This isn't free. Anything you run on the login node is not charged, but anything you submit to the batch system, to the compute nodes, will be charged. So just be aware of that when you're writing your batch scripts, that you're not requesting more resources accidentally than you actually require, because all this charge is coming back to the DESC repo. There's a question back there.
Yeah, just out of curiosity, does the debug queue charge as well?
Debug queue charges as well, yes. The shared queue only charges per core, not per compute node, so it can be really handy to submit your jobs there because you only charge by the core.
One thing I was like to think about the shared queue is it seems that there's hyper-threading and then it really shows at 64, and so we charge, are we really getting 2 CPUs or 1 CPU? What's going on?
You're charged in the shared queue, you are charged by the core. So
you get 1 core even though it has 2 hyper-threads on it.
Yeah.
You might get, if you submitted 2, okay, never mind.
Yep. Okay, so, and that's it. So there's more information here. I will just point out that we have our annual meeting in a week or two, which is actually rather good timing because there's new user training on the 21st. If you're unable to attend in person or remotely, if you're interested in that, then there's also all the slides. Vast amount of information about how to use NERSC resources designed for new users will be on the web at this place. So check that out. Cool. Thank you.
So while June set up the question. Yeah, one of the problems I've been having is the queue time seems like it's very low. Like 5, 6 days, 10 days.
Well, it depends on what you're requesting, what resources you're requesting, but yes, it can be a long time waiting if that is true. And if you do find that you're taking a really long time with queue, sort of more than 2 days, for example, then it's worth sending a ticket and asking what's going on. Because there may be problems involved. The turnaround time in the DESC queue is usually a couple of minutes. It averages something like 8 minutes. The shared queue is very popular, and so there tends to be a lot of backup in the shared queue. And that's the thing that we're definitely aware of in NERSC, and we're actively working to improve. Yeah.
Just following that up, is there a rough rule which is does queue time scale more with the number of nodes or with time requested, or are they affect people?
They're equally weighted.
Okay.
So I was just looking at your slides and the comment on how to get access to this allocation.
Yeah.
So the description here is if you're logging on to this site, if you already have an account, how do you get access? I couldn't find it immediately.
You already have an account. I believe that you need to contact the PI. So contact Richard or Peter, and they will add you manually.
Which one is that? Okay, so if you guys don't know me, my name is Jim Chiang. I'm a software developer here at Slack. Before I joined the LSST project and the DESC collaboration, I was a software developer on the sharing project where I wrote a lot of the science analysis code. So I've been asked by the computing infrastructure group to give a presentation describing some recommended practices to help you guys write better code. Since a lot of our scientific output is going to rely almost entirely on software, I think we need to write as good a code as possible in order to make sure that our scientific output is as good as it can be. So to do that, I boiled it down to 3 sort of takeaway messages, which I'll go into detail, give you the whys and hows to do these things, and then I'll give some demos of how to use some of the tools that Andy mentioned to put these takeaways into actual practice. So the first thing, just as a reference, all this material is described at this Confluence page. So if you have questions after the talk and want to dig deeper into anything that I say today, you can go to this page and have a look. So the first thing is testing. So I know right now everybody tests their code. If you write a piece of code and you run it and you look at the output, you're testing your code. Now, some people may be more rigorous about this. If they're doing a complicated calculation, they may be testing against theoretical expectations. And that's great. And you may even provide little test programs that's packaged with your code that users are supposed to run and look at the output. And this provides also an example of how to use your code, and that's also great. But I think if you're going to have other people rely upon your code, or they're going to rely upon results that are coming out of your code, the code itself really needs to be tested thoroughly and systematically. And to my mind, this also means that the tests have to be automated. So what does automated mean? So in this context, automated means that the tests are self-verifying. In other words, you don't have to look at the output to see that it's correct, and that they have to be, they can be run without any special setup. So if your code is, if your package is installed, you can just type run tests, and they go, and hopefully everything works. And the reason why it's important to have the tests automated this way is that even for extremely well-designed, loosely coupled code, any new developments, any bug fixes, anything like that can potentially break something that already works. And so you want to be able to have these tests to guard against that eventuality. And another reason for doing testing is because a comprehensive set of tests, especially unit tests, allow you to refactor. And if I had my druthers and were to add a fourth point to this list, it would be that we should do as much refactoring as possible. And refactoring means just improving the code while not necessarily changing the functionality. Okay, and this is something which is incredibly important if you want to write maintainable, reliable code. So how do you automate your tests? So there are lots of different ways of testing code. There are these different things I mentioned up here, system integration and so forth. You can look online to see what these things mean. The things I want to talk about today are unit tests, and that's because these bear most directly on your daily activities as a developer. Okay, so what are unit tests? So unit tests test the functionality of the smallest units of code. In this case, that means functions and class methods. And the way it does this, the most natural way would be to write a test running some function with some input and check the output and see that it matches your expectation. And so you should do that for all the functions in your code. But you should also check for failure. For example, if you have bad input and you know there's some range of input that's bad, then that function or class should raise an exception or produce some sort of error message. You should also check for consistency. So if you have a function and you have the implementation of its inverse, you should check the composition of those two operations brings you back to where you were before. Or if you write out a file to persist some complicated data structure, you should be able to read that in and check that the data structure you read back in matches the one that you persisted originally. So there are a number of things to keep in mind in writing your tests. The first thing is that the unit test should be quick and easy to execute. And that means that they should also be run throughout the development cycle. And the other thing is that the output of tests should be minimal. So if you have to look at the output of the test to see that it was successful, then you'll run the test less often, or you won't be as careful as checking the output to make sure the test ran correctly. You should consider test-first development, especially for fixing bugs. Good strategy is if you encounter a bug, write a test that exposes that bug, and then once you verify that the existing code fails that test, fix the code to make it pass, and then keep that test in your test suite thereafter. There's this notion of 100% coverage, and that's the ideal. In other words, you have all of the functions in your code tested. But time is a finite resource. We can't test every single bit of our code. So if I were to say to test the things in your code, you should test the things which have the greatest cost of failure. And it may be a simple function, but if a lot of your code relies on this simple function, that simple function should be tested. And finally,
sorry, would you expand that a little bit more? The greatest cost of failure?
Okay, well, so for example, you have some function which is straightforward to implement. It just reads some data structure, something like that. And returns it. If every bit of your code uses that particular function, everywhere, if that thing fails, then all of your code base fails. It may be a simple thing to implement. It may be straightforward. You may not think it needs testing, but because it's so important, you should test it. So you don't necessarily test the things that are most likely to break. You test the things that, if they break, they cause you the most problems. Okay. So I'm going to give an example here of some code in this repository that I put in my area called test prices. Very simple class here. And so this is writing a unit test or a set of tests for this function called isPrime. This module just has one function that tests if a number is prime. And so I'm using this unit test module in Python. I'm importing this function from my little package here, and I'm subclassing this class called test case in the unit test module. And so I'm writing a test for each of these cases. I'm testing the case whether one is prime. And the nice thing about this test case class, it gives you these methods for asserting whether some test fails or not. So is prime is one is not a prime. So I want to use the assert fails here. I'm testing test 2 is prime, assert true. And I'm also testing for failure, as I mentioned before. The prime test should only operate on natural numbers. So if I give it a float, it should raise a type error, which it does. So this is sort of a trivial example, but this is the type of testing I'm talking about. Testing the smallest sort of function within your code base and making sure it behaves as you expected in all these different ways. There's more interesting examples here you can see in the Twickles repository, which is too big an example to put up here. The next recommended practice I like to talk about is reading other people's code and having them read your code. This could be boiled down to just sharing your code. Now, as scientists, most of us have picked up software development on our own. We haven't been trained in any formal way in the sort of standard practices that have evolved over time to make code more reliable. And even though this practice can be taught, most of us, as I said, picked them up on our own, and not necessarily have had the best examples to learn from. However, there are a bunch of people among us who take the craft of coding very seriously. So it's good to look at their code and see what they did and ask them for help on how to make their own code better. Another reason for looking at other people's code and commenting on their code is that not everyone approaches a coding task exactly the same way. So having different eyes on a problem can often lead to better implementation because there's something someone else may think of that you haven't thought of. And then finally, for a group software project, if you only have one person who knows how to maintain a certain bit of code, it's extremely dangerous to just have all that knowledge residing in one person. So that's a huge source of risk. So the more that knowledge is spread around by reading other people's code, the better. So what can you do to share your code? So here's some suggestions. The first one is obvious. Put it on GitHub, someplace where your colleagues, at least in DESC, can see it. This is the easiest way to make your code available for others to read and try out. The next suggestion is to do code reviews. So code reviews in this context means just for any new bit of development, whether it's a bug fix or a new feature, have someone come and look at your code in a formal way and make sure it makes sense, make sure it's well documented, the formatting is correct, and it's readable and understandable. And if you do this incrementally for each of these small bits of changes, it's actually relatively painless. There's a link here to the DM team's description of what entails code review, so I encourage you to go have a look at that. Another thing you can do is pair program. I don't have a lot of experience with this, but it makes sense that having people with different programming backgrounds, both in terms of what they've done and in terms of their different levels of experience working together, can help spread the knowledge around within a collaboration. The next thing you could do, that I list here, is have different people cycle through working on bits of code. This can be somewhat controversial because I know people are used to sort of owning a bit of code and saying, this is what I've developed, and I'm the best person to maintain it. But I think having people cycle through different parts of code will help, again, spread that knowledge around and avoid that risk of having just one person maintain one bit of code. Okay. And so the next recommendation is to have a set of coding conventions. Okay, so at the tutorial yesterday, Andy mentioned that he had worked with Jake Vanderplas on a lot of the code that was supporting their book on doing statistical analyses of survey data using Python. So they wrote a lot of Python code together, but they have very different coding styles. In particular, from what I understand, Jake likes to do things in sort of very fancy, maybe not obvious ways, and they didn't comment their code very well. And so Andy went back to look at this code a year later, and he couldn't understand what was going on. So he had to copy a section of the code out, put it into Google, and search on it to see what it was doing. So the point here is that, even though you're working in the same language, if you speak vastly different dialects or have vastly different coding styles, you're not going to really understand what each other is doing. So it's good to have a set of conventions. And so as far as I'm concerned, you should look at the standard conventions and just simply adopt those. For Python, this is PEP 8. And PEP 8 is standard for a reason, and a lot of the conventions they have, just sort of make sense in terms of, not just things like indentation and white space usage, but also coding idioms, which are more reliable and which make more sense in the use of the language. But whatever you do, reach a consensus, at least within the group or project that you're working on, a set of standard conventions that you all obey. You can help this by using code checking tools, these so-called linters. And there's this tool called Pilot, which I will demo, which basically applies the PEP 8 standards to your code, and you can run it inside of an editor, and it shows you where all your flaws in your code are. You can go and fix those things. And so you should use these plugins in your editor, whether it's Emacs or Vim or some fancy IDE like PyCharm, to run these code checking tools. So that you can get used to applying these conventions in your software. So let me stop there and go into the demos. The first demo I'd like to do is just showing you how to use GitHub Flow to do development within your project. Now, a development workflow is designed to avoid conflicts. So if you have any sort of project where there's more than a couple developers in there, then having some sort of development workflow is necessary to avoid putting conflicting changes into your repository. It's also extremely essential if you want people to use your code at the master level. In other words, you want people to use the most cutting edge version of your code, so that the so-called master branch is always deployable in this model. and any development you do is done on these side branches so that master is not contaminated by bad code. So as an example, we'll fix a bug in this primes repository, which I'm going to show you later. So the first step in GitHub flow, if you're working on a bug, for example, is just create a branch off of master. So these are the commands at the command line. I do git branch to show that I'm a master. I do a pull to make sure I'm up to date with what's there. And then I do a git checkout -b, and then the name of the branch. And the branch should be some descriptive name. And your group may have some convention for associating with a ticket or an issue in the repository. And so once you're on the branch, then it's safe to start doing development. So as I said, in this case, we want to fix a bug. And so the first thing I would do here is edit the test code in this testprimes.py file and write a test case which exercises this bug. For example, like I showed you before, to check the floating point raises a type error or something like that. And then once I've run the code and verified that the new test fails in the existing code as it is, then I'm going to add this change to Git and then commit it. Okay. And then once I have the test in place, I want to edit the production code to fix it. So this is going to be to repair the bug right there. And at that point, once I fix the code, I want to run all of the tests, not just the test that failed, to verify that the code is still in working order. And then I'm going to add that to the repository, make the commit. Okay. And so once you've done all your work, you can push your changes to GitHub. So that's what I'm doing here. Since I created a new branch, you have to do this -u origin and then the branch name to tell it its development on the new branch. And at that point, it's there on GitHub. Okay. So if you go to the web interface, you can go and open a pull request. And a pull request can actually be issued at any time. It doesn't have to be issued right when you're ready for your changes to be merged or when you want a code review. You can open a pull request on a branch that doesn't have complete development on it if you want to ask people about what should I do next. So here we are at the primes repository. Here you are at the new branch. You can pull down this menu to select the branch that you want to issue the pull request on, and you can click this button and issue a pull request. And so at the pull request thread, you'll be asked to make some comments. I'm sorry you can't read this very well. So basically what I've done here is shown so I'm showing what the error was originally that I'm fixing, okay? And then if you click on this Files Change tab here, you can actually go to the files and make comments on the code if you want to do code review. And I'll show you a live example of that once I bring it up in the browser. So, and then basically once all the tests pass and the reviewer is satisfied with your changes, you can merge it into master. There's a button down here for merge pull request, and then you're done. Okay, and in principle, master on your repository works. There may be a separate stage of running integration tests if you want to run integration tests to make sure it works with other bits of code that rely on your code. But basically, that's the full development workflow. Okay. So the next thing I want to do is show you some of these tools used live, and I'll do it within the Emacs editor. Let me get out of this and bring up Emacs. Okay. Okay. Okay, so here's Emacs. And so what I have here, yay. Thank you, Tim. Yeah, so I have the test. This is the full test code for this primes package that I showed you. And let's see, so I hooked up a couple of keyboard bindings to do various things. So I can, for example, if I do Control-C, this will run this program called nose tests. And nose test basically runs all the unit tests within a package. And the reason why I use nose is because you can hook it up to Emacs, so it's convenient. So in this case, there's a failure. And if you hit Control-X backtick, which is a standard next error in Emacs, it takes you to the place where the failure occurred. Okay, so there's this assertion error. So here, basically, I'm testing that, for example, that isPrime raises a type error if the number is less than or equal to 0, because those are not natural numbers. That should be a failure. Okay, so that's one thing. I can also show you, so let's do some editing, and I can show you another tool. So there's this tool called Jedi, which is an auto-completion tool. It's also a code checking tool, but it actually does command completion. So let's write a new test. Test 7 is prime. So every time you see code in here in gray, I'm hitting tab, and that's part of the completion the Jedi is doing for me. So here's assert equals. I don't actually want assert equals. I want assert true is prime 7. Okay, so before I run the test, let me run Pylint on this. So Pylint is one of these linters. It applies the PEP8 standards to it and tells you where you've gone wrong. So let me add a couple of sort of bad conventions here, put some arbitrary white space in. So here I bound it to Control-C, Control-P. So it finds all these errors. If you can do Control backtick, which is next error, it takes you to where the first error is. So there's extraneous white space here. Do the next one. There's white space here, which I can get rid of. Here, there's no doc string, so I can add a doc string. P, oops, sorry. And so it passes. And so you get this report from Pylint, which has a bunch of statistics telling you basically how good your code is, number of duplicated lines, how you've obeyed the conventions from iteration to iteration, and it gives you a final rating on your code. So, yeah.
Can you say a little more about how you integrate Pylint into Emacs?
Yeah. So if you go, so on this page here, these are links to these. There's a link here to the DM page to describe how to set it up in your .emacs file, so you can integrate all these tools. And then there's some link for there. Okay, so let's actually fix this test as long as we're here. So I'm going to go to the actual production code. So it's in Python, DESC, prime. Okay, so this is the full test. So the reason why it broke is because I had commented out this if thing, which raises a type error. So I can run Pylint there, it passes. Hit Control-C, Control-C to run those tests, and everything passes. So you're done.
Does it tell you if this all right here, which is a warning, which is an error?
So you mean for nose? So nose test will tell you Pylint. Oh, okay, yeah. I mean, so Pylint basically just issues warnings, right? It's just checking your code. I think if you actually do have a syntax error, so let me stick a syntax error in here. Get rid of that. Oops, sorry. Yeah, so if you have a syntax error, it'll tell you that it's an actual error as opposed to just a formatting error. Okay. So that's a nice thing again about these tools. They'll do static type checking to check things like whether a variable's been declared, whether you're importing a deprecated package, stuff like that. So it's an incredibly useful thing to have. Okay, so I got 5 minutes left. Let me show you now how to connect your GitHub repository to Travis CI, which is a continuous integration tool. If I can ever. Okay. So the first thing you do is go to your repository. So I have this primes package that I was using in my demo. Go to settings. And under settings, go under webhooks and services. Under add service, oops, sorry. There's a whole bunch of services there, so you can just search for Travis. Oops. Travis CI. And it fills this in for you, and all you have to do is just hit add service. Okay, so this is now hooked up to Travis CI. You can edit the configuration to see what's going on. So that's on the GitHub side. On the Travis CI side, you have to log in, and then see. Okay, for some reason I don't see all of my repositories. Okay, I think because of the, okay, for some reason, okay, there should be on the left-hand side here a list of repositories. Unfortunately, I can't show you in this demo because I can't access that part of the browser right now. But in any case, what you would do is you would go to basically the settings for where all your repositories are connected in GitHub. Turn on Travis CI for that repository. You can set configurations such that it triggers builds off of pushes or pull requests. And then basically you're done. You can go back here and either trigger a build manually, which is what this would do. So it would send a payload over the Travis CI, or if you were actually doing development and you did a push or a merge or whatever, it would trigger off of that and it would do a build automatically, and you would get the results over here. And just to show you an example, this is this monitor package within DESC, which had a failed build. I guess I won't go into the details here. Oh, one other thing, in your repository, you need to set up a Travis CI configuration file. And I'll just show you that here really quickly. So it's this .travis.yml file, which is in the main folder of the repository. And here you set the language, which version. If you have requirements you need to install using pip, you can do that. You can list them in this requirements.txt file. We don't need that for this repo. If there's any setup or building you need to do, like running make or whatever, you can put that here. And then the script here is the scripts that should be running to do your tests. So this would be the continuous integration part. So anyway, that's the demo of Travis CI. So let me stop because I'm out of time and just throw up my summary talks here and stop there for questions. Thank you very much.
So I'm willing to accept that I don't do things the best way, but I've typically taken my testing from a top-down approach. So I would test like the end product and then see, okay, if that's working for you, then work my way down. Is there a way that you recommend? What's the main reason for doing like the more incremental and test versus?
Well, I mean, I think you should do both, really. So the type of test you're talking about is more of a system test, right? So you have some large code base, you're checking the outputs and making sure it makes sense, maybe checking against some standard data product, for example. And that's fine. I think you should do that. The thing is, if you're making an incremental change, it's incredibly difficult to run something like that to make sure you didn't break something. And for something like that, it's really hard to comprehensively test every bit of the interfaces within your code. So if you have unit tests, especially at the package level, then you can make sure that things, work and you're not introducing new bugs with new development, anything like that. So I think you should do both, really. But like I said, when I'm doing development and I'm fixing a new bug, I'm running unit tests every time I save the file, basically, if I think it's worth running. So if you're doing this huge system test, you can't work that way. It's too complicated.
Jim, if we want to run something which is relatively more complicated, like let's say it relies on the stack or something, did either you or somebody from DM, if you guys set up something, I don't know, like a document file or something that we could use with Travis CI so that I can run my programs? That sounds like something would be.
Okay, so Mario was just mentioning that the Conda installations can install potentially, at Travis CI if the images are small enough, there's enough space, and it does it fast enough that it can work within Travis.
Somehow in that YAML file, I can
just
Conda install.
I don't know disrespect to the next speaker, but depending on how interesting the next speaker is, you may have that. I'm looking at it.
So I think actually we have to bring this to a close because there's another session in this room 2 minutes ago. So let's thank everyone for